Humanity's story is one of constant innovation. We invent, we improve, we push boundaries. From the wheel to the internet, each leap forward reshapes our world. Now, a new revolution dawns: quantum computing. This is not just an upgrade, it's a fundamental shift in how we understand and interact with information itself. Imagine a future where the impossible becomes possible. Drug discovery is accelerated. Materials with unheard-of properties are engineered. The very fabric of reality is simulated with perfect accuracy. This is the promise of quantum computing. But to grasp its power, we must first journey back to the origins of the technology that came before. This journey begins with classical computing. This technology, for all its sophistication, relies on simple principles. Bits, like tiny switches, are either on or off, representing 1 or 0. These bits combine to form the language of computers. But as our ambition grew, we hit a wall. Classical computers struggle with the complexity of the quantum world. To break through this barrier, we must turn to the very science that makes quantum computing possible: quantum mechanics. This is where the familiar rules of physics break down, replaced by a realm of uncertainty and mind-bending possibilities. Chapter 2. The Classical Computing Era. The 20th century saw the rise of the classical computer. Transistors, tiny electrical switches, became the building blocks of a new era. These transistors, etched onto silicon chips, gave rise to the computers we know today. From room-sized behemoths to sleek smartphones, classical computers have transformed our world. They process information as bits, like tiny switches flipping between 0 and 1. This binary code underpins everything from spreadsheets to video games, yet this simplicity comes at a cost. Classical computers excel at tasks that can be broken down into logical steps, but they falter when faced with the messy, interconnected world of atoms and molecules. As transistors shrank, approaching the size of atoms, a new problem emerged. The predictable laws of classical physics no longer applied in this subatomic realm. Instead, a stranger, more counterintuitive set of rules governed these tiny particles: the laws of quantum mechanics. This is not just an academic curiosity, it's a fundamental limit to classical computing. To simulate the quantum world, to design new drugs or understand the fundamental nature of materials, we need a new kind of computer. Chapter 3. Entering the Quantum Realm. In the early 20th century, physics underwent a revolution. Scientists like Einstein, Bohr, and Heisenberg unveiled a hidden reality operating beneath the surface of our everyday experience. This is the quantum realm, a place where particles can be in multiple states at once, where information seems to travel faster than light. One of the most bizarre aspects of quantum mechanics is superposition. Imagine a coin spinning in the air, neither heads nor tails until it lands. That's what it's like for a quantum particle. It exists in a blurry combination of states until we measure it. This is not just theoretical. Experiments have confirmed these strange behaviors time and again. Equally mind-boggling is entanglement. Two entangled particles are linked, no matter how far apart they are. Change the state of one, and the other changes instantly, as if by magic. Einstein famously called this spooky action at a distance. These quantum phenomena, once confined to the realm of theoretical physics, are now at the heart of a technological revolution. Could we harness superposition and entanglement to build a new kind of computer, one that operates on the very principles of the quantum world? Chapter 4. Pioneering the Quantum Computer. The idea of a quantum computer remained a distant dream for decades. Then, in the 1980s, physicists like Richard Feynman and David Deutsch began to lay the theoretical groundwork. Feynman, known for his playful genius, argued that classical computers were fundamentally ill-suited to simulating quantum systems. He proposed a radical solution: build computers that operate on quantum principles themselves. Around the same time, David Deutsch formalized the concept of a universal quantum computer. This wouldn't just be a faster classical computer, it would be a fundamentally different kind of machine, capable of solving problems that would take classical computers billions of years. The key to this power lies in the qubit. Unlike a bit, which is either 0 or 1, a qubit can be in a superposition of both states simultaneously. This allows quantum computers to explore many possibilities at once, giving them an enormous speed advantage for certain tasks. But building a quantum computer is like trying to build a castle out of clouds. Qubits are incredibly fragile. The slightest disturbance can destroy their delicate quantum states. Yet, undeterred, scientists and engineers began to tackle this challenge, driven by the promise of what quantum computing could achieve. Chapter 5. Building the first quantum machines. The first quantum computers were rudimentary, to say the least. They consisted of a handful of qubits, painstakingly trapped and manipulated using lasers and magnetic fields. Maintaining these qubits in their quantum states required extreme conditions, often just a fraction of a degree above absolute zero. Imagine a laboratory filled with lasers, mirrors, and vacuum chambers, all working in concert to control the state of a few atoms. This is the reality of early quantum computing research. It was a time of trial and error, of pushing the limits of what was technologically possible. Despite the challenges, progress was steady. In the 1990s, researchers demonstrated the first quantum logic gates, the building blocks of quantum circuits. These gates allowed them to perform simple operations on qubits, paving the way for more complex computations. The field was still in its infancy, but the potential was clear. Countries like the United States, China, and members of the European Union, along with corporations such as Google, IBM, Microsoft, Amazon, and China's Alibaba, are fiercely competing in the race for quantum supremacy to secure technological, economic, and strategic advantages. Quantum computing has the potential to transform technology, solve previously unsolvable problems, and redefine global power through breakthroughs in science, security, and innovation. In 2019, we witnessed a groundbreaking moment in the field of quantum computing. Google announced that its quantum computer, Sycamore, had achieved quantum supremacy. This means it performed a specific task faster than the most powerful classical supercomputers. It was a monumental milestone, marking the dawn of a new era in computational capabilities. While this achievement is just one step on a long journey, it undeniably showcased the immense potential of quantum technology. In October 2024, IBM opened its first quantum data center in Europe, located in Enningen, Germany. This facility houses IBM's most advanced quantum systems, including the Heron processor, and aims to accelerate quantum research and development across the continent. The future, it seems, is quantum. As we delve deeper into quantum computing, two critical challenges emerge: stability and scalability. Maintaining quantum states, or qubits, without errors is incredibly difficult due to environmental interference. And scaling these systems to perform complex computations remains a significant hurdle. Yet researchers are making strides, developing innovative techniques to stabilize qubits and build more scalable quantum systems. This progress is bringing us closer to harnessing the full potential of quantum computing. Quantum computing holds immense promise, but it also comes with potential perils. On one hand, it could revolutionize fields like cryptography, medicine, and artificial intelligence, solving problems that are currently insurmountable. On the other hand, it poses risks, such as breaking existing encryption methods, which could compromise global security. Balancing these promises and perils is crucial as we advance in this cutting-edge technology. Quantum computing isn't just about faster calculations. It's about gaining a new understanding of reality itself. The principles of superposition and entanglement challenge our classical notions of how the world works. This new perspective could lead to breakthroughs in physics, chemistry, and beyond, revealing the universe in ways we can scarcely imagine today. We stand at the dawn of a quantum era. The progress we've made so far is just the beginning. As quantum technologies continue to evolve, they will reshape industries, economies, and perhaps even our daily lives. The journey ahead is filled with challenges, but the potential rewards are immense. Welcome to the future. Welcome to the quantum era.